applied, GMPA, etc. He was PI from the France on the project PDE control within the Indo-French Center for Applied Mathematics, IPCAM. He has been awarded several research grants. His research articles has the remarkable quality of being accessible to the very beginners, yet maintaining their advanced standard throughout. I suggest young researchers to see his books, that monograph on numerical approximation of exact controls for waves, and his excellent slide on Carleman estimate for elliptic PDE and applications. Today, he will be speaking on insensitizing control for the heat equation with respect to boundary variations. I hope you will enjoy the talk thoroughly. Professor Eberza, it's over to you now.
Well, thank you very much, Ashandu, for this very nice introduction. I should say that indeed I was a PI of a project with India, and I was very glad at that time to have strong exchanges with colleagues from India, and in particular from TIF in Bangalore. So it is my pleasure and honor to be here, or at least virtually today, and to do the last talk of the year, if I understood correctly. So I will present a joint work with Pierre Lissy, who is in Paris, in Serenade, and Yannick Privat in Strasbourg, on insensitizing controls for the heat equation with respect to boundary variations. So the title might seem a bit technical, and well, my first goal will be to explain you what I mean by this very long and technical title. So here it is. I will spend some time to introduce the problem and try to present the question, and then I will jump to the proof and comment it later. Okay. So my goal is today to present our understanding of insensitization properties for a functional which involve the solution of the heat equation. So I will be slightly more precise soon. But really the question of insensitization is the following one. So you have a system that you consider, which might be, so in our case, it would be the heat equation, but it might be a more complex system like Navier-Stokes equations or wave equations or Lamy equations, so depending on what you are considering. And what you want to do is to control that system, but you have some unknown parameters. So these unknowns might be of several kinds. So it can be in the initial datum, it can be in the source terms, some pollution in the source term, or things like that. So in fact, it has been popularized in a book by Lyons in '92 about the Sentinel question. And there have been a lot of articles since, depending on the quantity of interest, okay, on how the control acts on the system. Of course, the system also is very important in these questions, and what unknowns are considered. So in the case I will talk about today, so the unknown will be in the boundary, okay, and I will consider the heat equation. So there are many notations that I need to introduce before that. So I'm very sorry because it might be difficult to follow because of this notation. So I will just try to take some time.
Sorry, Professor Sylvain.
Yes.
Just sorry to interrupt you. Did you change your slide? Because we are still on the first slide.
Yes, I am. I don't know why it doesn't.
We are still seeing your first slide where you had the title of the talk actually.
Do you see my slide?
Yeah, only the first slide.
Yes, only the first slide.
Okay.
And now it is okay.
Now it came to full, but before that, nothing. And it is not in full screen mode.
Okay, and if I go in full screen, sorry, you see?
No, it's not full screen, right? Something is coming.
Okay, so let me, okay. I will try with another up.
Does Control L work?
Yeah, normally yes, but it seems that it does not.
Maybe, yeah, let's try again.
So here you see my screen normally.
Yeah. Now
Yes. Now it is full screen. Yes, now it's fine.
Okay. Okay, so maybe I should restart a little bit on insensitization. So my goal today is, well, I'm sorry, I will say it again, right? But my goal today is to try to understand insensitization properties for a functional which depend on the solution of a heat equation. And so this question of insensitization has been popularized by Lyons around the 90s. And the question is to control a system such that a quantity of interest, so we have to define what is a quantity of interest in the system under consideration, is not sensitive to some unknowns. Okay, so as I said, there might be several quantity of interest that you can consider, several type of unknowns you can consider. So in many works, the unknowns are in the source terms or in the initial data. And of course, there are many different systems that you can consider, and the results you will be able to obtain will depend strongly on the system you consider. Okay, so my goal is to control a system such that the quantity is not sensitive to some unknowns. So today, I will consider a heat equation. So here's the heat equation, right? My control will be H. And with this control, what I would like to do is to make this functional GH of omega insensitive with respect to variations of omega. Okay, so there are a lot of notations in that slide, so I will take some time just to make it fully precise. So there is a time t, which will be something fixed, some positive constant, and that's all. Okay, there are many sets. So these are domains of Rd. So there's small omega. Small omega is the control set. So here you see in the heat equation, we will have dty minus Laplacian y, so this is the heat equation, equal to some source term. Okay, this source term is here, which is a given thing, a given function. Okay, and what you want to do is to design a control H such that this is insensitive with respect to variations of omega, right? So omega is the control set, capital theta here appears there, right? So it appears as the observation set, right? So in fact, this functional is the L2 norm of your solution in the set theta, right? So theta is the observation set. Okay, so we have a control set, omega, an observation set, theta, and we have the domains where the equation takes place, which is omega, right? So at the end, this functional g here depends on omega, right? Because the solution here, y of omega h, depends on the set omega where the equation takes place, right? And it depends on h, which is the control function here acting on small omega. Okay, so here again, so in blue you have everything which is linked to the control, right? So H is the control. We will choose it in L2 in time with value in L2 of small omega. Okay, so omega is the control set and H is the control, and it appears here in an additive manner in the heat equation, as a source term in the heat equation. Theta, it's the observation set, and it appears only here, right, in the functional we want to insensitize. And omega, so the set in which the equation takes place, we assume it to be a known, or at least to have an unknown boundary, right? And this is precisely what will make this problem relevant here, is that on omega we have roughly the shape of the domain, okay, but we don't really know how is it precisely. Okay, so here, just before going further, I would like to comment on this functional GH of omega. So here we simply take the L2 norm of the solution in some observation set. So it can be thought as a kind of an energy localized in theta. And so somehow you want this energy localized in the set theta not to depend too much on variations of the boundary. Right. Okay, so again, so here I just rewrite this functional. And so again, theta, the observation set, omega is the control set. And my goal is to insensitize G, meaning that I want to choose a control, H, such that the functional GH does not depend on omega, or at least does not depend too much. Of course, as you can imagine, if omega varies strongly, the solution Y will strongly vary, and it will be very difficult. So what we will do here is only a local result, and then so we are going to provide a framework to analyze this functional for small variations of omega, and of course small variation of its boundary. Okay, so to present this framework, okay, I see that there are some. Okay, is omega fixed? Yes, omega is fixed. So yeah, I didn't see the question before. I hope it's still okay. So yes, the domain small omega is fixed. Okay, so let me give the framework to consider variations of omega. So in fact, the framework is quite classical. It's the framework of shape optimization. So there are many textbooks on it. Here, well, I give the reference to the book of Antoine Henrot and Michel Pierre in 2005, which I really like, but there are others, of course. So here in this case, so we have to, again, to introduce some notation. So we have, okay, what I will present here is shape optimization. So I will try to differentiate around some domain omega 0, right? So this omega 0, I will assume that it has some regularity. So it will be C2. And then what I will do is use a vector field V and see how it deforms my domain omega 0. So for tau small, so tau is a real parameter which is small, I consider this domain omega tau v, which is the image by identity plus tau v of omega 0. So if tau is small enough, this guy, identity plus tau v, is a diffeomorphism, right? And so omega tau v is simply the image of omega 0 by a diffeomorphism, right? So in particular, it will have the same properties of omega 0, like connectedness and so on. Okay, so at least for tau small. Okay, and thus we can look at the map which to tau associate GH of omega of 2V, and this map will be differentiable, right? So this is really the framework of shape optimization. And if you try to compute it, so here we cover, so we had the integral of 1/2 y squared, right? So of course, when you differentiate, you get y times the differentiate of y with respect to the domain, which is this y dot v, right? So y omega 0 h is the control solution in the domain omega 0, right? So of course, it depends on h through that source term. And y dot v is the differentiation of basically this guy, right, with respect to the domain. And so what you see is that it solves a heat equation with 0 initial condition and some non-trivial boundary term, right, which involves v dot n and the flux dn y0 on the boundary. Okay, so this computation is quite classical, but okay, it's really interesting to see how it works. Okay, so once you have this, you can. Right, this is not. This is still not so practical to deal with. So you can use adjoints, and this is something which has been done precisely in the work by Lissi, Priva, and Simpore that I will talk about soon. So you can compute it, can compute this derivative more precisely using the adjoint, and you'll have that, in fact, this derivative can be written as the integral over d omega 0, so over the boundary of omega 0, of v dot n against something, some quantity. So here you see you are very close to having a gradient formulation, right? So this guy can be thought as a gradient of your functional, right? And this guy, what is it? It's dny0, dnz0. So y0 again, it solves the heat equation with source term xi and h, the control, right? So this y0 depends on h. And z0 is simply the solution of the backward heat equation which is coupled to y0 through the observation set. Okay, so it's maybe important to notice that here, in this formulation of the derivative of gh, the set capital theta, which was used in the definition of gh, right, does not appear explicitly here anymore. It appears in the definition of z0 only, right, in this place, through the coupling between y0 and z0. Okay, so this formula will be more useful and more comfortable to deal with. Okay. So what are the questions I will consider? So I have this functional GH. I have explained to you how we will differentiate that, right? And the questions I will try to focus on are the questions of exact insensitization with respect to the boundary, which means that I want to find a control H such that for all vector fields, the derivative of GH in the direction of this vector field is 0. Okay, so as we will see, this will be quite difficult to achieve, right? So we will also consider a relaxed formulation of this question, which we call approximate insensitization with respect to the boundary, which is the following one. For all epsilon positive, we want to find a control H such that for all vector field, the derivative of GH in the direction of the vector field is bounded by epsilon times the norm of V. Okay, so as we will see, this one is easier to achieve. Okay, what should I say? Well, maybe I should say that in the following, I will speak about exact insensitization and approximate insensitization, and that will always deal with insensitization with respect to the boundary, but I will omit that quite often. Okay. So let me try to present our results. So the first thing to realize when you consider this, this problem is that somehow the geometry will matter, and you have to consider the relative position of omega, theta, and capital omega. And as we will see, in fact, probably the results strongly differ depending whether omega intersected with theta is empty or not. Okay, so I will present two theorems. So here's the theorem one. So again, I should mention that all these results are obtained as a joint work with Pierre Lucie and Yannick Privat. So the first case, consider omega intersected with theta, which is empty. Okay, and capital theta is strongly included in omega 0, right? And omega 0 minus the closure of theta is a connected set. Okay, so I will come back to these assumptions. But under these assumptions, what we have is approximate insensitization. This holds, no problem. And we may also further impose exact insensitization on a finite dimensional subspace of the vector field. Okay, so I will present the proof and try to give you the main insights about it. But it will be based on basically two results. So one is an approximate controllability result, which is not completely standard, and a bilinear argument, because I will emphasize that, in fact, what makes this control problem difficult is that it is a bilinear control problem. Okay. So let me just mention what can be done in when omega intersected with theta is not empty. So in fact, this case is easier because somehow you are controlling on the observation set, right? So it makes sense even from the intuition that it should be easier. Okay, so in that case, indeed, we can prove much more results. We can prove that approximate insensitization holds, so as before, that we can also, as before, further impose exact insensitization on a finite dimensional subspace. Okay, and we may also impose that the control we will construct is an approximate control at final time. That is, if we consider a target function yf, we can guarantee, we can choose the control h such that our solution y0 at time t is close to yf at the end. Okay, so here we make precise the topology we are working on, right? So here it should be L2 of omega 0, sorry about that. But we want that the norm of y0 at time t minus yf in the norm of L2 of omega 0 is smaller than epsilon. Okay, and in fact, we can even go further. And so this is only for people who are interested on this question, because I will not talk about much. I don't have time to explain it in detail. But if you have a source stem psi, which can be null control, meaning that there exists a null control without regarding the functional and so on, then in fact you can choose a null control which also realize approximate insensitization of the functional and exact insensitization on a finite dimensional subspace of deformations. Okay, so again, the proof will be based on the same ingredients. So an approximate controllability result, which as it turns out will be easier in that case than in the previous case, and a bilinear control argument. Okay, so in fact, all these works with Pierre Lissy and Yannick Privat are based on a first work which has been done by Lissy, Privat, and Simporé, which provides in the above geometrical case, in which omega intersected with theta is not empty, approximate insensitization and exact insensitization on a vector space of dimension 1 or 2. So here the difference is that we managed to consider the case in which omega intersected with theta is empty. And also we do not have this restriction on the vector space on which we want to impose exact insensitization. Okay, so in fact, it turns out that our proof of exact insensitization will be completely different than what they did in this work. And this is why we are able to generalize it a lot. Okay, so let me try to explain the proof. So, so here I'm considering theorem 1. And so theorem 1 is the case in which omega intersected with theta is empty. So in principle, this is a delicate case in which you do not control where you observe. Okay. The first question is the question of approximate insensitization. So to deal with that, I will just recall what is the derivative of this function. So this is the integral of v dot n against the integral over time of dny0 dnz0, where y0 solves this heat equation and z0 solves this backward heat equation. So of course the difficulty here is that with one control, you want to control a forward heat equation and a backward heat equation through the coupling. Right? So this is a coupled parabolic system, and you have only one control. Okay, so this is a question which has been studied a lot in many situations. But maybe here in this case, it's important to notice that what we really want to control is not y0 or z0. What we want to control is the product of dny0 times dnz0. Right? So in fact, when I vary h, so y0 depends linearly on h, right? Z0 depends linearly on h, but then this guy here depends quadratically on h, right? So this is not really a linear control problem. Still, our first strategy to be able to realize approximate insensitization is quite simple, which will be to choose h such that this guy and this guy are small. Okay, so such that dny0 is small and dnz0 is small. So we will call it approximate controllability, even if usually approximate controllability refers to the possibility to making the solution small at time capital T in the domain omega, right? While here we are trying to make the solution small on the boundary, right? Okay, so this is not really the usual approximate controllability, but this question here can really be thought as an approximate controllability problem. Okay, and so it is clear that if we manage to get control H such that the norm of dny0, dnz0 is smaller than square root of epsilon, then the product here is smaller than epsilon, and at the end of the day, you will have that the derivative of this functional will be smaller than epsilon times the norm of v in L infinity. Okay, so here's the approximate controllability results we have, and this is where the geometry will appear in a critical manner. Okay, so in this approximate controllability result, we have omega intersected with theta, which is empty. So omega is a subset of capital omega. Theta is strongly included in omega. And omega minus the closure of theta is connected. So then what we have is the following. So I call it approximate controllability result, but again, this is not the classical approximate controllability statements. So we have for all data, fy and fz, which are functions on the boundary, right? For all epsilon positive, we can construct a control function h localized in omega, right? So control appears here, such that the solution yz, so of your coupled system, okay, so y again, so y solves the forward heat equation, z solves the backward heat equation coupled to y. Then you have that the norm of dny, dnz minus fyfz is smaller than epsilon. Okay, so how to prove that? Well, to prove that, in fact, it's quite standard, right? We have a linear map, which to a functional to a function h localized in omega, so h is your control, maps dny dnz, where y is the solution of the previous, y and z are the solutions of the previous system. Okay, and the question is, can you guarantee that the range of that map is dense in L2 of 0t with values L2 of the boundary? Okay, and well, this is a standard fact of functional analysis that if you want to show that the range of a linear operator is dense, then it's usually easier to deal with the kernel of the adjoint, right? So to prove that, what we are going to prove is that the kernel of L star equals to 0. So then basically what I have to do is to express what is L star, and to check then that the kernel of L star is 0. So L star, it takes two elements, g psi and g phi, which are functions of the boundary, right? Which each of them belong to L2 0t, L2 d omega. And L star of g psi, g phi is psi localized on omega, where psi and phi solve these equations. So what are these? Okay, so in fact, probably you should start from there, right? You should start from below. So you solve first the heat equation in 0t cross omega, starting from 0, right? With a non-homogeneous Dirichlet boundary data, phi equal to g phi on the boundary. Okay, so once you have phi, you solve the three equations on top, right? So this is the backward heat equation, okay, which is coupled. Okay, so here we see the coupling with on the set theta, right? So which is coupled with the solution phi, and this psi also has some non-homogeneous Dirichlet boundary conditions. Okay, and the question, so this computation of L star is very standard, so I will not detail it here. But then the question, so for the kernel of L star to be 0 is, if psi equal to 0 in 0t cross omega, do we necessarily have that g psi and g phi are 0? So let me explain that and emphasize the geometrical conditions that will appear in there. So we have that psi is equal to 0 in 0t cross omega. And then psi, we know that it solves the backward heat equation here. Okay, and in there are two terms that we do not know. There is the source term, on which so far we have nothing, right? And there is the boundary term, on which so far I know nothing. Okay, but here there's an indicative function, right? So in fact, the source term vanishes outside of theta, right? And so in fact, your solution psi satisfies the backward heat equation with no source term in omega minus theta. Okay, and you know that psi equal to 0 in 0t cross omega. And you also know that omega intersected with theta is empty. So in fact, you know that you have an open set in omega minus theta in which psi vanish, and psi satisfies the backward heat equation there. So then by standard unit continuation for the heat equation, you have that psi vanishes in omega minus theta. Okay, and besides that, since theta is strongly included in omega, you necessarily have that psi is 0 close to the boundary, right? So close to the boundary of omega. Okay, so this means that g psi is necessarily 0, and that psi is 0 in the neighborhood of the boundary. So now you look at the equation satisfied by phi, which is written here in item 2, right? So phi satisfies this equation. And you know that psi is already, so it satisfies this equation, and that psi vanishes close to the boundary of omega. So what you do is quite simple. You multiply the equation of psi by phi, right? So you will have the integral of 0t, the integral of theta of phi square coming from there. And then you have that it equals to minus d psi over dt minus Laplacian psi against phi. You do integration by parts. You have no boundary terms because psi vanishes in the neighborhood of the boundary of omega, right? And because psi at time t and phi at time 0 vanishes as well. Okay, so you get that this quantity is 0. So phi is 0, sorry, there's a misprint, in 0t cross theta, and phi satisfies the heat equation with no source term, right? So then again, by standard unit continuation, you get that phi vanishes everywhere in omega and g phi equal to 0. Okay. So using these arguments, you will have approximate insensitization. And so the next question I promised to address is what about exact insensitization? So it might be quite technical if I introduce all the notations and so on. So I will try to explain it when the finite dimensional subspace is a subspace of dimension 1, okay, which makes it much easier to explain. But it's important that this strategy can be really generalized to any finite dimensional vector space. Okay, so again, we will use several steps. So the first step is to approximately insensitize your function. So in order to do that, we use the previous step, right? So we choose a control H0 such that dny0, dnz0 is smaller than square root of epsilon. Okay, where y0 and z0 solves these two equations. So y0 is the forward heat equation with control H0, right? And the other one is the backward heat equation with the coupling here with y0. Okay, so once we have that, we are almost there, right? So we are doing a mistake on V1, but this mistake is of the order of epsilon, right? So now what I am doing is simply replace psi by psi plus H0 because it doesn't change anything, and look for an additional control H, which will be small, but we will see that at the end, which will correct the error I can do on the derivative of GH in the direction of V1. Okay, so this control H, I want to use that such that I get exact insensitization with respect to the direction V1, meaning that I have this property that the integral on the boundary of V1 dot n against this quantity here equals to 0, right? There, where Y solves again, so it's the heat equation with the source term psi, the control H, and Z satisfies the backward heat equation with this coupling term here on the observation set theta. So again, I want to emphasize that this is a bilinear control problem, right? Because Y will depend linearly on H, Z depends linearly on Y and thus on H. Okay, so dny times dnz will depend in a quadratic manner of H. Okay, so to better emphasize that, I simply separate in Y what depends really linearly on H and what depends on the data psi, right? So, okay, it makes another set of equation. It's getting painful. I agree with the number of notations and so on. But, oh, I see I have questions, right? How do I see the question?
You can take it at the end itself, if you
Okay,
prefer.
I will take it at the end.
Okay.
Okay, so here you see y psi and z psi depends only on the data psi, right? And in fact, we already know, because we have modified psi a little bit, that dn of y psi and dn of z psi are small. Okay, but this choice is done, so I will not play with that anymore. And I have part of the solution which depend on H, right? So here the dependence is truly linear, while in the other case it was affine. Okay, so YH really is the solution corresponding to a source term H localized in omega, right? And ZH is the backward heat equation with this coupling. Okay. So then when I look at the guy I want to cancel, there are several terms. So I decompose really Y as YH plus Y psi and Z as ZH plus Z psi. So there are several terms. Okay, but what is important is that this first term here is a quadratic form, right? The second one is, so it's a quadratic in H, right? Again, YH is linear in H, ZH is linear in H. This one does not depend on H, okay? And this one does not depend on H. Okay, so this is quadratic in H, this is linear in H, and this is a constant which depends only on psi. Okay, so what we have to do is to find zeros of a quadratic form. So we know how to do that, right? We learned that when we were students in school. Okay, so the difficulty is that if we look for H in a 1D vector space, which is a priori the natural thing to do, so we look for H as lambda under the form lambda times H1 with H1 fixed and lambda in R. Then you'll have to cancel a functional that looks like lambda square Q of H1 plus lambda of L of H1 plus some constant. And so this is a quadratic polynomial. And the problem is that if you are not lucky, this guy could never vanish. It might happen. Okay, and in fact, this is also related to several issues that have been discussed very recently in a close context by Bochard and Marbach in 2018 and much more developed since then, where they proved that basically when you want to control an ODE in which the linearized system is not controllable. So it's very natural to go at second order, but then if you go at second order, most of the time you will fail controlling, simply because, well, with a scalar control, right? So in these works, we are looking at controllability issues with a scalar control. It's very important. So with a scalar control, basically what you will see is that if you go at second order approximation, you will always remain on a manifold, and you will not be able to control your solution in the whole space. Okay, so here it's more or less the same. If we consider scalar controls, meaning that it is on a line, right, the vector space of dimension 1, then you will fail. Well, most of the time you will fail, right? Okay, so the idea is in fact very simple, is to consider H in a two-dimensional vector space. Okay, so it might be surprising at first, because what we have is one constraint, right? What we want to do is to satisfy one constraint. And for this one-dimensional constraint, so for this one constraint, we will look for the control H in the two-dimensional vector space. And so if we do that, so H will be of the form lambda 1 H1 plus lambda 2 H2, with lambda 1 and lambda 2, which are real numbers. If you do that, and if we manage to impose that this quadratic form on lambda 1 H1 plus lambda 2 H2 is of the form of lambda 1 lambda 2, then we know that we will be able to control simply by taking lambda 2 equal to modulus of lambda 1, right? Because then somehow, well, I will explain it later, but you will have, you will be able to conclude by the intermediate value theorem. Okay, so in fact, here again, this is an idea which is very close to something we did with Chaudhuri in 2019. And probably we were addressing these issues with these ideas because we did that before. Okay, so in these works with Chaudhuri, what we did was to control the Navier-Stokes equation in a channel with controls acting only on the normal component. So it might seem to be quite different, and it is, but it turns out that this is precisely a case where when you linearize, the equations are not controllable. So what we did in that work is to go at the second order expansion and use the fact that somehow the nonlinearity of the Navier-Stokes equation will realize that property by itself. Okay, so this was really, in fact, the key point of the arguments we developed with Cherchendou in this article, which is now published in. Well. Okay. So let's have a look at this operator Q of lambda 1 H1 plus lambda 2 H2. So in fact, if we want to impose Q of lambda 1 H1 plus lambda 2 H2 equal to lambda 1 lambda 2, what we do is, again, decompose our solutions YH as Y H1, as lambda 1 Y H1, plus lambda 2 Y H2, right? This is linear in H, so we do that. And so what we want is that Q of H1 equal to 0, Q of H2 equal to 0, and the bilinear form, which is here, has to be equal to 1. So this is the cross product. Okay, so can we do that? Well, here it's quite easy to check that we can do that. So we can, well, we can set gamma 1 y like this, okay, gamma 1 z like this, gamma 2 y like this, and gamma 2 z like this. So what are the properties of this guy? The properties of this guy is that if you replace dny h1 by this, dn z h1 by this, dn yh2 by this and dn zh2 by this, you'll have these properties. So let me just check this one. So this one, so you do the multiplication of dny h1 dnz h1. So you see here, this is supported in time on 0t/2, and this one is supported in time on t/2t. So this cross product here is zero all the time, right? So this is 0. Okay, of course, it's completely similar for this one. So what about this one? This one here, so dny h1, dnz h2. So I have to look at this guy against this guy. So here you see on time, on 0t/2, this is constant. Okay, equal to 1/t times v1.n. So this one depends only on x, divided by that. Okay, so when you integrate in time, at least for the first term here, you will have v1.n divided by the norm of v1.n square over 2. Okay, and of course you'll have the same with the other one. And so then you understand that this here is only to normalize because you have this v1.n in front. And so at the end you get 1. Okay, so of course the problem is that you cannot really choose dny_h1 and all the flux here to be like this, but we have the approximate controllability result, right? So we can choose this guy to be very close to this gamma 1y, gamma 1z, gamma 2y, gamma 2z. Okay, and this is enough for our argument because we will have that. So for instance, for all lambda in R, the quadratic form, when it is applied to lambda h1 plus modulus of lambda h2 minus lambda of modulus of lambda is smaller than lambda square over 2. So once you have that, it's easy to check that this quadratic form here, so you see I'm looking at this on lambda h1 plus modulus of lambda h2, so in the quadratic form and in the linear form. So this map here is a function which goes to plus infinity when lambda goes to plus infinity. It goes to minus infinity when lambda goes to minus infinity. And of course, it is continuous. So it necessarily has to vanish by the intermediate value theorem. Okay, and beside that, you can have estimate on lambda, which will involve this parameter here, 6i. And as I told you, this 6i, in fact, depends only on dny0 and dnz0, which we choose already to be small. Okay, so of course, we have to play a little bit with the epsilon to have the correct statement, but then it's done. Okay, so when you see that, you understand that if you have a finite dimensional space, what you will do is consider, so if this finite dimensional space is of dimension m, for instance, you will consider controls which are in a 2m vector space, 2m dimensional vector space, and you will be able to do more or less the same, except that it will not be as simple as one function, right, with values in R, because you will have m constraints, right? So in fact, you will consider a functional which goes from Rm to Rm, and you will be able to conclude using Brouwer fixed point theorem, for instance. Okay. Okay, so let me jump now to the proof of theorem 2. So again, this is supposed to be the easy case, right? So this is the case in which the control set omega intersects the observation set capital theta. And then the question is more or less the same, right? So we will use an approximate controllability result and everything will be based on that. So what is this approximate controllability result? Well, it's more or less the same as before, except that now I am mentioning that I can also approximately control y at time t, right? So here again, omega intersected with theta is not empty. And what we have in that case is that for all pairs of function on the boundary fy and fz for all target state yf, and for all epsilon positive, we can find a control h localized in small omega, such that the solution yz of this intricate system of heat equations. So again, here this is the forward heat equation controlled by H. Here this is the backward heat equation, which is coupled to Y, okay? And the control here does not act directly, okay? It only acts in an indirect manner through this coupling set, okay? Then for this solution YZ, we will be able to guarantee that dNy, dNz minus is close to fyfz on the boundary, right, in this norm, and that y at time t is close to yf in this norm. Okay, the proof again, it's more or less, it's very similar to the one before, right? So we introduce the linear map which to H associate dNy, dNz, and yt. We want to analyze if the range of this linear map is dense. So we look at the adjoint. Okay, so we compute the adjoint, which is L star, which is here, right? So the adjoint now takes three terms, right? So two functions which are on the boundary, and one function which is in L2 of omega, which would be the final data of psi. Okay, and L star of g psi, g phi, psi t will be psi localized in omega. So what about psi? Psi satisfies, no, sorry, again, so you have to start with the equations below. So phi satisfies the forward heat equation with a boundary, non-homogeneous boundary data g phi, right? On the other hand, psi satisfies the backward heat equation with data at time t, which is non-zero, which is psi t, right? Non-homogeneous boundary data g psi, and the coupling here with the solution of phi. So again, the question is, if psi equal to 0 in 0t cross omega, do we have that g psi, g phi, and psi t all vanish? Okay, and in fact, it's much easier because now omega intersected with theta is not empty. So if psi is 0 in that set, you see immediately from the equation that phi will vanish in omega intersected with theta, right? So this comes immediately from the equation. Okay, then phi satisfies the heat equation with no source term. Okay, it has non-homogeneous Dirichlet boundary data, but it is known by unique continuation for the heat equation that if phi vanishes in some open subset, then everything is 0. And in particular, the boundary data g phi is 0. So now, since phi equal to 0, you have that psi satisfies the backward heat equation with no source term. And again, we know that psi is 0 in 0t cross omega. Okay, thus, again, we simply use the unique continuation property for the heat equation, and we deduce that psi vanishes identically in 0t cross omega, that g psi equal to 0 and that psi t vanish. Okay, so once we have that, the proof of theorem 2 is completely similar to the one of theorem 1, so I will not explain it further. I just want to point out that the approximate controllability result we have is slightly stronger in this case, and of course we can use that to prove all the statements of theorem 2. So in particular, let me recall that in this statement, I was saying that we could prove approximate insensitization and approximate controllability at time t simultaneously, right? And that we could further impose exact insensitization on a finite dimensional vector space. So again, the proof here are completely similar to the ones I gave before for theorem 1, except that they will now rely on this stronger approximate controllability result. Now I just want to do one remark. If the source stem xi is null controllable, we can also further impose that y0 at time capital T is 0. But we need to be slightly more careful and to revisit even more the approximate controllability result. So I don't want to go through it more precisely, but I just want to mention for people who are more used to consider null controllability issues, that in fact it means that we can construct that if some source term can be null control, then we can further impose we can further impose that null control will make our functional insensitized with respect to variations with respect to the boundary, right? Which is quite new, I would say. Okay, so I think my time is almost over, so I'll try to finish it now. So I just want to add a couple of remarks. So about exact insensitization, this is much more delicate. So what we do is exact insensitization with respect to finite dimensional vector space. On exact insensitization, on exact insensitization with respect to all variations of the boundary, we have only partial results, which are more or less straightforward. So the first one is exact insensitization holds if the set theta is strongly embedded in omega. In fact, it's not difficult to check, because in that case, we can make Z0 to vanish close to the boundary of capital omega. So exact insensitization is also possible when d theta is included in omega, and capital theta is strongly included in omega 0. So this is basically the same type of argument as the previous case. Okay. What we know, on the other hand, is that exact insensitization is not possible if omega 0 is smooth, the observation set theta is omega 0, and the control set omega is strictly included in omega naught. And in fact, to do that, it's very simple. This is based on regularity issues. So if you control in omega, in fact, the only modifications you would be able to do on the boundary is modification by smooth functions, right? So everything is based on that. So I don't want to go into too many details, but really this one is an easy case. So what is clear from this discussion is that so far we do not have a clear geometrical condition for exact insensitization. So this is really an open problem. Okay, but there are many other related open problems. So the first one is that in the case in which omega intersected theta is empty, we had results which are weaker than in the case in which the intersection is non-empty. Okay, in particular, in the case in which the intersection is empty, we are not able to say, for the moment at least, if we can further impose approximate or null controllability at time t. And that would be interesting. So I just want to emphasize that our approach is really based on controlling linear equations, right? While in fact, what we want is to control some quantity which is bilinear. So maybe there's something which can be done which takes into account more precisely these quadratic aspects. Okay. Also, what can be done for functionals involving solution of over equations? So for instance, if you consider the wave equation, what can you do? Okay, so far we have no clue at all. Well, probably it will strongly depend again on some unique continuation properties for coupled wave equations. So there are, in fact, many results on control issues for wave equations. So maybe one should go there. But yeah, so far it's quite open. Okay, of course, the functional we consider here is very basic, right? Is the L2 norm in some set theta, but we could try to consider more general functional and see what happens. And so far we have no clue about that. Okay, so thank you for your attention. I will stop here. We try to take the question, but well, okay, well, thank you. Okay, so how do we read the questions?
Okay, I will read, Sylvain, the questions. So first of all, thank you, Professor Ivedeza, for this wonderful talk. And now I request all the participants to write their question in question answer box. We already have some questions, so I am going to read it for you.
Okay, thank you. Yeah, I see that.
So many. So the first one is, will the analysis be same if we consider the following cases? Non-zero initial condition, non-zero boundary condition, other boundary condition, include the nonlinearity in the equation.
Okay, so there are many questions. So I guess that non-zero initial condition could be considered similarly. When you consider boundary conditions, you have to be a bit careful because you will be differentiating with respect to the boundary, right? So you have to explain precisely what it means to differentiate with respect to the boundary when you have non-zero boundary conditions. Okay, so in fact, this is also the same for item 3, right? So when you consider other boundary conditions, you have to be able also to understand what it means to differentiate with respect to the boundary, right? The functional, to differentiate the functional with respect to the boundary. Okay, and so I guess, for instance, for Neumann boundary conditions, probably the same analysis apply. But if you go to more sophisticated things like Robin boundary conditions or Wenzel boundary conditions or stuff like that, well, probably you should be careful, I would say. Include nonlinearity in the equation. That's a very good question. It's probably very delicate to do. In fact, the work by Prival ici and Simpore that I was referring to was also dealing with semi-linearity heat equations. And so basically what they did was based on linear arguments, so as we have, but maybe it would be more delicate to get exact insensitization in this case. Okay.
So just nonlinearity means in that case, global ellipsis nonlinearity or any other kind of nonlinearity?
Well, global ellipsis semi-linearity would be already something new.
Okay.
Okay.
Okay. So then the other, okay.
For the regularity of omega 0, again, we use that only to be in the framework of shape optimization. Right, so we use that omega 0 was C2 and that the vector fields were W3 infinity because this is the classical framework of shape optimization. So if you want to go below that, well, you have to understand what it means to differentiate with respect to variations of the boundary. So I do not really understand the question 2 on linear variation with respect to the parameter tau. In fact, when you have a vector field, you can also consider a diffeomorphism, which in some sense is the deformation of your domain on the action of the vector field V, right? So there are other possible ways to define such diffeomorphism, but at the end, they all look at what happens in the normal direction V dot n on the boundary. So, okay, for the wave equation, as I told you at the end, this is quite open. We have unique continuation property in some cases, but it is more intricate. And of course, propagation will matter. And so there are several results on the controllability of coupled wave equations. So I remember, for instance, there's a result by Deman, Leoto, and Le Rousseau on these questions. So probably there are some ideas there that could be used to deal as well with the case of wave equation of, okay. Okay, so I have many questions, in fact. Okay, thank you. If I want to make G insensitive to the set O. Well, this is a good question, indeed. I don't know. I didn't think about that. So what is maybe relevant in that, in fact, is that most of the time when we study null controllability issues or approximate controllability issues, we want the control to satisfy one objective. But what happens if we want the control to satisfy several objectives? What can be done in that case? Okay, so for instance, could be insensitize the functional G with respect to O and the variations of the external boundary omega? I have no idea. And can we do that and further impose that we get null controllability at the end? I don't know. But this is a very good question indeed. Okay. For SPD or differential inclusions, I have no clue. In fact, I'm not sure to understand what you mean precisely.
There is
probably you have to make the problem more explicit, because for stochastic PDE there will be some expected value somewhere, I guess.
Yes, I was just curious because, you know, it's wonderful, great talk, of course. Thank you very much. Wonderful that, you know, you exhibited this insensitivity in the case of, you know, the heat equation and this choice of functional, which was quite enlightening. So I was just curious in terms of other kinds of differential equations. So, you know, SPDs, or in the other case of differential inclusions, which in some sense is a broader kind of notion of differential equation as well. So I was just curious if you might have an interest in that.
Well, in fact, I really don't know. About differential inclusions, I guess you assume uniqueness at least, right? Uniqueness of the solutions, because the functional needs to be well-defined. And at least for the approach we choose here, we have to be able to consider some kind of differential structure on the functional. So I don't know if we can really do that with differential inclusions. Maybe, well, I'm not aware of that.
Yes, thank you.
And what is the next question with respect to a hyperplane in the domain? What do you mean?
So in the analysis, you know, it wasn't, you have the functional being insensitized with respect to a boundary. So I was just thinking how perhaps you can consider the more broad question of insensitization with respect to any subset. of interest, really,
Mhm.
just the boundary.
Well, so I think this is quite close to the question by when my Biswas on insensitization with respect to theta, to the observation set. To be honest, I didn't check that. I didn't consider that question, but I guess it can be done probably, but it needs to be done.
Yes, thank you.
Sylvain, there is a question in the chat box. So it's written that did you obtain similar results for the degenerate PDEs? So you may open the chat box. It's written.
Yeah. Okay.
Florida.
So thank you, Giuseppe, for this question. So what is clear? What is clear is that in the arguments we have developed, in fact, we are only using unique continuation for the heat equation, right? We are not using analyticity properties and stuff like that. So in fact, as soon as you have unique continuation, it should work. So I'm not sure to know what kind of degenerate PD you want to consider. Of course, it will depend if the degeneracy is on the boundary on which you differentiate, because then you have to be extremely careful to express the derivative of the functional close to that boundary, right? But if your variations on the boundary are somewhere in which the equation is not degenerate, probably everything should work.
Thank you very much for the answers. Thanks.
Okay.
Thank you, Sylvain, for all the question answer session. So now, so thanks to all participants and the speakers to make this webinar series successful. Our special thanks goes to Kaushik Mohanto, Firoz SK, and Purvita Jana for their help throughout. So we encourage you to provide your valuable feedback in email or orally if you want to say right now. So how the webinar overall this series, if you want to say something now. Okay, in that case, you may write down your feedback in email. So now I want to share the screen to point out something. So what we have noticed, just 1 second. So just 1 second. So I hope you are able to see the screen. Is it visible?
Yes, it is.
So what we have noticed that the 4 institutes which organize this event in some way in the 4 different parts of the India, the 4 different corners from north, south, and east and west. So this is just an observation. So again, I thanks to all, and we hope that we will able to organize something in the next year, some similar kind of webinar series. So till then, I thanks everybody, and I request all to leave the platform now. So goodbye for the time being.
Goodbye, Professor Sylvain.
Well, thank you for the organization, and I hope it was okay. And I wish you all good holidays and Merry Christmas.
Yeah.
Okay.
Merry Christmas.
Bye.
See you. Bye-bye.